Thank you very much for the introduction. Thanks for the invitation to be here today. It's absolutely delightful to see how much activity there is at EPFL. I actually spent a month here back in 2009 visiting Alfredo and his group and had a great time, and it's was already extremely impressive at that time, and it's even more impressive now to see how much that is going on. So the work that I'm going to be talking about today has been done by the people who are listed here. On the first row are the people who are still, or at least until recently, were at UCSB in my group, and then Cyrus Dreyer, Anderson Gianotti, Audrius Alkauskas, and Jack Lyons and Chimin Yan in the meantime have moved on to other positions. So, what we do in my group is first principles calculations. Not all of you are theorists, I assume. Don't worry, I tend to not dwell on all of the calculational details. I tend to show very few equations in my talks. I prefer to talk about the physics, okay? And, but of course, I do want to put it into the context of the power of first principles calculations that is available now. What we want to achieve is a fundamental description of what's going on in a solid. And what you need for that is to do quantum mechanics on electrons. And of course, there are many electrons in the solid. So this is a horrendously complicated many-body problem, which you cannot possibly solve exactly. You can solve the hydrogen atom exactly. You can solve very small molecules more or less exactly. Beyond a few atoms, beyond 10 electrons or so, you need approximations. And of course, the most effective approximation that's available in this field is to use density functional theory, which actually, in principle, isn't even an approximation. Walter Kohn, who sadly passed away last year, showed us that with density functional theory, you can actually have a rigorous description of the quantum mechanics of the electron problem in a solid, not by solving for all of the wave functions of the electrons individually, but actually by using the charge density of the electrons as the fundamental quantity. That is a rigorous statement. In principle, you can formulate a Schrödinger equation for one electron that moves in an effective potential that includes the effects of all of the other electrons. Where the approximations lie is in determining what that effective potential is, which is done in terms of a functional of the charge density. And traditionally, the functionals that were used for that led to inaccuracies in the description of the electronic structure, the most well-known of which is the underestimation of the band gap of semiconductors and insulators. In recent years, a lot of progress has been made in this respect. What we now use are so-called hybrid functionals, which give us an excellent description of the electronic structure, an excellent description of the atomic structure, and also with the advantage of being able to treat problems that involve carrier localization. I will show you some examples of this in this talk, that situations where the electron density is not very smooth, but where the electrons tend to localize in one particular site, can be accurately described with this sort of functional. So, by and large, density functional theory offers us an extremely powerful machinery for calculating and predicting materials properties without any input or fitting to experiment. Okay. And this has now led to the capability to use density functional theory for so-called high throughput computation or computationally guided materials design, where you look at a bunch of possible materials, either materials that are already known or materials that may yet have to be synthesized, and you try to pick the ones that are going to have specific properties. Okay. And then if that pans out, hopefully those can be experimentally synthesized. So there is a lot of work going on in this area, and on this slide I've put some of the most important centers worldwide that are engaged in this sort of effort, both in terms of creating databases of materials properties, or setting up a platform for people to use codes for their own computations, sometimes a combination of these things. Of course, the AIDA one is the local one here, which is very well known. And this is a very worthwhile effort that I think will increasingly gain importance in the field of materials. What I want to focus on in this talk is that as part of this effort, we need to be very careful about phrasing the questions that we want the computations to answer. Okay. When you do these calculations and when you screen for materials properties, you have to formulate what the question is to which you want some kind of answer. Okay? A simple one would be, what is the band gap of a material to determine whether it's going to be a metal or a semiconductor or a wide band gap insulator. And as I already alluded to, if you use density functional theory and if you don't use a reliable functional, you may not actually get the right answer. So that's something to worry about. But I want to talk more broadly about situations where, in order to screen for new materials, we need to make sure we are focusing on the correct questions in terms of actually having a correct understanding of the underlying physics. Okay. Only when we have that understanding will our first principles calculations actually be useful in giving us the answers that we're looking for. At the same time, I'd like to show that by doing first principles calculations, we can actually help in generating that understanding and in elucidating the correct physics. So, we need to have a thorough knowledge of the underlying physics, because if you don't have a complete understanding, you could actually sadly be wasting a lot of time, personal time as well as computer time, by doing misguided searches. So I will illustrate these points with two case studies. Case study number one. I tried to kind of pick different topics because I knew this would be a diverse audience. So there will be something on oxides, and there will be something that is more related to semiconductors that are used as light emitters. So first topic has to do with oxides, the value of the Mott-Hubbard gap. Okay, so I'm particularly talking about so-called complex-oxides, a very large class of which has the perovskite structure. These are compounds with composition AbO3. Okay, typically B is a transition metal. Typically, these materials have a cubic structure or a structure that is somewhat distorted from this basic cube. with the B atom sitting at the center of the cube. It is octahedrally coordinated by oxygen atoms, so these oxygens sit at the centers of the faces of the cube, and then the A atom sits at the corners of the cube. Okay, so maybe the most well-known prototype example of this is strontium titanate. It's kind of the prototype complex oxide. Another example is lanthanum aluminate. These perovskites have been studied for decades because they have many, many interesting properties, electronic properties as well as structural properties. They can be used as high-K dielectrics. They have interesting magnetic properties, ferroelectricity, you name it. they seem to exhibit all kinds of interesting functional properties that of course make them very attractive for all kinds of applications. Now about a little over 10 years ago, a very interesting discovery was made that kind of reignited interest in this field, namely the discovery of a spontaneous formation of a two-dimensional electron gas at the interface between two of these oxides. So that's why I mentioned strontium titanate and lanthanum aluminate. Both of these materials have large band gaps. Particularly lanthanum aluminate is essentially an insulator, 5.6 eV band gap. Strontium titanate has a band gap of 3.2 eV, and so in principle is not naturally conducting, but you put these two materials together, you put a thin layer of lanthanum aluminate on top of strontium titanate, and lo and behold, a sheet of electrons spontaneously forms at the interface with an electron density of 10 to the 13th per square centimeter. If that number doesn't mean much to you, that's a very high number, okay? That's like an order of magnitude higher than what you get in silicon transistors, on which all of silicon technology is based. And it's on about the same order as what you get in nitride devices, which a lot of people here are working on. But in nitride devices, you work very hard to generate the correct structures to actually give you such a two-dimensional electron gas. Here, it kind of happened spontaneously. Okay, so this obviously created a high degree of interest, and we started working on this, and actually had quite some success in explaining what the source of that two-dimensional electron gas is, which I don't have time to go into now. But in the process of all of that work, it actually became obvious that 10 to the 13th is only the beginning of it. If you use different materials combinations, in particular, if you use gadolinium titanate rather than strontium titanate to form the heterojunction, you can actually get even an order of magnitude higher, 10 to the 14th electrons per square centimeter, okay? And this was beautifully demonstrated in the group of Professor Suzanne Stemmer at UCSB, where they grew these very high quality interfaces, and they demonstrated by doing measurements of the sheet carrier concentration that they indeed had this very high density of electrons present. Okay, so the interfaces kind of form a whole area of research in their own right, but that's not what I'm going to focus on. I wanted to use this as an introduction to our studies of gadolinium titanate, which is a very interesting material in its own right. How do we think about gadolinium titanate? Well, I mentioned strontium titanate, okay? The strontium atom there, it supplies some electrons, but really doesn't play much of a role in the electronic structure. The band structure of strontium titanate, which is really just a relatively easy to understand insulator, consists of a valence band that is dominated by oxygen p states, and a conduction band that is dominated by titanium d states. Okay. So we understand this material. We can kind of understand what the charge balance is in this material. Titanium has a valence 4. Strontium has a valence 2. That gives you 6 electrons available, which of course are being grabbed by these 3 oxygen atoms, 2 electrons for each oxygen atom. It's kind of the octet rule. So we understand this. Now we move to gadolinium titanate. Okay, so again, the valence strontium is 2+. Gadolinium turns out, I mean, it's a complicated rare earth, but effectively it behaves as an atom with a valence 3+, okay, which means that you have 1 extra electron available. Where does that electron go? Well, we think we understand the band structure, so this electron needs to go in the conduction band, right? So you expect this material to be a metal. What actually happens is that these electrons do not simply fill this conduction band, but they localize. Remember, I mentioned localization early on and the importance of describing this. It turns out that in this material, it's more energetically favorable for electrons to localize in one particular titanium D state and kind of form a separate band by themselves, which is then separated from what you can call the actual conduction band by a band gap. Okay. So this is a Mott-insulator, first described by Sir Neville Mott, to explain why a material that you would expect to be a metal, just based on electron counting, actually behaves as an insulator. Okay, so that's the material we're interested in. And this material has been known and studied for decades, so we thought when we started doing calculations that we could just look at the experimental literature and that we would find everything there is to know about this material. That turned out not to be true. So here are the sort of calculations that we do. I told you that this simple cubic structure is only like a template for the perovskites. In many of these materials, you actually get distortions of these oxygen octahedra that lead to larger unit cells. So instead of a 5-atom unit cell in gadolinium titanate, you have a 20-atom orthorhombic unit cell. We can calculate the structure accurately, and we can calculate the electronic structure. At the top is for strontium titanate. That's a complete band structure. It has this band gap of 3.2 eV that I talked about. And here's what we calculate for gadolinium titanate. And yeah, you see this band gap opening up. I've labeled here the so-called lower Hubbard band, which is this set of filled titanium D states that splits off. And then what is now actually the conduction band is the upper Hubbard band, okay? And then you have this Mott-Hubbard gap in between, okay? So just to take a step back, there is a lot of interest in materials that exhibit this so-called Mott physics, okay? Where you have, in principle, a metallic state, but the material turns insulating. And let me just briefly explain why that is. I mean, people are constantly looking for new materials that would at least supplement silicon in technology, right? And silicon, of course, works very well, but as you know, one of the problems with silicon is that if you try to keep making more and more transistors on a chip, you generate a lot of heat, right? I mean, if you put your laptop actually on your lap, you may burn yourself, right? So there is a search for materials that can actually operate as transistors, but with a fundamental mechanism that would be different from silicon and that would lead to higher current densities without so much dissipation. And the idea of having materials that maybe in some way could be switched between a true metallic state and a true insulating state is very appealing in this context. It would lead to a novel type of transistor structure. So there are many, many materials that in principle exhibit some sort of transition like this. And so people are really interested in being able to screen materials either experimentally or computationally based on their properties with regard to this metal-insulator transition. And this is why being able to determine what the size of that gap is that makes it an insulator is an important problem. Okay, so this is essentially a repetition of what I said initially about using density functional theory, hybrid functional, etc. This is the machinery that we use to calculate this band structure of gadolinium titanate. And so what's our result? We find that the separation between the occupied states and the unoccupied states, the so-called Mott-Hubbard gap, is approximately 2 electron volts, a really nice large value. Okay, so that's our result, and we tried to publish this, and we got a lot of pushback. Okay, to the extent, and I'll come back to the reason why we got a lot of pushback, but it kind of forced us to say, well, okay, we can't just publish this computational result. Let's try and get an experimental verification. So we talked to people who have a lot of experience in characterizing material, particularly the group of Professor Devdeep Jena at Cornell University, and they actually did photoluminescence experiments as well as photoluminescence excitation. And they actually got strong luminescence out of this. This was material, again, grown by the group of Professor Suzanne Stemmer. Very thin layers, okay? I think this was on the order of 100 nanometer thick layer, so really not much material. But they got luminescence out that was visible with the naked eye. And the luminescence occurred at about 1.8 eV. Not quite the same as 2 eV, but very close, I think, within the computational error bar to what is found experimentally. Okay, so very strong red luminescence. So we eventually got the paper published by showing that our computational prediction did actually match this experimental value. So why did we initially get pushback? It's because lots of people, including referees, were telling us that 2 eV had to be completely wrong, and because it was very well known that the gap of gadolinium titanate was not 2 eV, but 0.7 eV. Lower by a factor of 3. Very, very different. No way to explain this by any sort of error bars or anything. So we started looking at what sort of experiments they were referring to that would produce this 0.7 eV gap. Okay. It turns out that those experiments are essentially optical absorption experiments. So not luminescence experiments, but I mean, it's actually done in the context of so-called optical conductivity, but it's essentially an optical absorption measurement in which you monitor the conductivity of the material as a function of photon energy, and at some point you see an onset, which in gadolinium titanate turns out to be at about 0.7 eV. Okay, so this sort of measurements is very prevalent in the literature, has been done on lots of different rare earth titanates, all with reasonably similar results, all giving a very low value on the order of half an eV for this onset. And this onset is interpreted as the gap. Okay? It's interpreted as the energy that you need for a photon to be able to excite an electron out of this lower Hubbard band into the upper Hubbard band. Okay. So in the community, it seems very well accepted that this is a measurement of the Mott-Hubbard gap, which would be very, very different from what we calculated or what was measured by photoluminescence. So we started thinking about where that discrepancy comes from, right? What is it actually that is being measured in this optical absorption experiment? Well, it's essentially a measurement of some kind of excitation, right? Sure, it could be an excitation from the lower Hubbard band to the upper Hubbard band, but maybe there are other excitation processes possible in this material. So this got us thinking, and what we got thinking about was polarons. Okay, so let me take 2 minutes for those of you who are not familiar with polarons to tell you a little bit about this. I was not familiar with polarons until about 5 years ago, when suddenly they started popping up in all kinds of research projects that we happen to be working on. Polarons very often occur in these oxides, actually mostly in terms of localization of holes. Okay. I told you that the valence band of these oxides is made up of oxygen p states. Now, when we think of the valence band of a conducting material, silicon or gallium arsenide, we usually, well, we always think of delocalized states, right? In which if you have a hole, a missing electron, it's going to be delocalized, it's going to be moving very easily through the material. But localization might happen, okay? Similar to what I was saying earlier about electrons getting localized on titanium atoms, here electrons could get, holes could get localized on oxygen atoms, okay? And that actually happens by having a distortion of the lattice, okay? So locally the atoms move, and that creates a lower energy state in which the hole can get trapped. And you can do calculations for this. My student Joel Varley did this for tin oxide some years ago, and you clearly see this localized state corresponding to a localized hole, which is referred to as a small polaron. Okay. Now you may think, of course, well, doesn't the necessity for lattice relaxations cost energy? It does, but as you probably all know, that's elastic energy that goes quadratically as a function of the displacement, whereas the energy gain due to the localization process is actually linear. So you solve a very simple equation and you find that the energy minimum actually occurs for a finite distortion for which you do find the localization. Okay, so polaron formation, well known for holes in oxides. It can also happen for electrons. Again, with the example of a titanium-containing compound, just simple TiO2, the walls are full of TiO2 here, white paint is full of TiO2 nanoparticles. Titanium localizes electrons in titanium oxide. It can be more favorable to put an electron in a localized state, which is a state within the band gap below the conduction band, more favorable than putting an electron in the conduction band. Okay. So polarons are very well known in these materials. And actually in gadolinium titanate, polarons form as well. So we started thinking about the consequences of having these polarons for excitation processes. Okay. So first of all, we verified that, yeah, these polarons are present. Actually, then we found out that experimentally, in work by the very famous John Goodenough, this had already been flagged as an issue for transport in gadolinium titanate and other rare earth titanates. And yeah, you put a hole, again, it's a small hole polaron. You put a hole in gadolinium titanate. It does not form a delocalized state. It wants to localize on a titanium atom. Okay. So this by itself is well established, not controversial at all. But what had not been explored was the effect of these polarons on optical absorption. Okay. And that's what we investigated. We did these supercell calculations in which one polaron is present. And we started looking at possible excitations. So one type of excitation is where you take a small polaron, localized, and take it to a delocalized state. Okay? So you can map this out in this so-called configuration coordinate diagram. The lower curve is for the small polaron. It's the more stable state. If you wanted to form a delocalized hole, which of course experimentally you have no control over, but in the calculations we can control these things. We can force the atomic positions to remain fixed to those of a perfect lattice, and then the hole is delocalized. And by comparing the energies of these two curves, we can see the amount of energy by which the small polaron is stabilized. That's about half a volt. Okay? And we can also see how much energy it would cost to take the small polaron state to the delocalized state. Okay? So that's one possible absorption process that we investigated, okay, whereby the polaron that's sitting on a particular site would become delocalized. Now, the other way in which a polaron might absorb light or be excited is by hopping from one site to another site, okay? And that's illustrated here. You have a polar on one side, you have a polar on another side. You analyze these curves in a similar way, and you get information about the excitation energy that you need to actually move this polaron. Okay. So we did a more elaborate analysis of this to actually map out what the optical absorption curve would look like as a function of photon energy to have these excitation processes. And actually the two processes maybe coincidentally produce very similar curves, which are illustrated on the right-hand side here. So as a function of photon energy, the amount of light you would absorb follows this sort of curve, and it actually shows an onset at about 0.7 electron volts. Remember the 0.7 electron volts that experimentally is always associated with the Mott-Hubbard gap based on these absorption experiments. We think that this is what people are measuring. They are not measuring an excitation of an electron from an occupied state to an unoccupied state. They are looking at material that, according to John Goodenough, is always containing small hole polarons because it tends to be unintentionally doped. And these small hole polarons absorb light with an onset as a function of photon energy that has been, in our opinion, erroneously interpreted as the magnitude of the gap. Okay. So again, we did more work on this in collaboration with Experiment. The group of Suzanne Stemmer actually grew intentionally doped samples in which the number of hole polarons could be controlled, and we actually found very good agreement between theory and experiment. So here's the bottom line. This rare earth titanate, gadolinium titanate, is a Mott-insulator. It's very well known. It's the magnitude of the gap that wasn't well known in our opinion. We say it's about 2 eV. That agrees extremely well with photoluminescence measurements. The controversy revolved around reconciling this number with the much smaller number that had been measured in optical absorption, but we can explain this by understanding the physics correctly. We can attribute the optical absorption to excitations of small polarons. Okay. So the bottom line for the purposes of this talk is that doing a particular experiment doesn't necessarily mean that you're addressing the actual quantity that you think you're measuring, right? You have to be very careful about thinking what it actually is that you're measuring in an experiment. Doesn't mean the experiment is wrong. We never criticize the experimental data. What we have questions about is what is the interpretation of that data, right? So you need to pay attention to the origin of what you measure, conductivity, absorption, etc. And such an understanding is then, in my opinion, essential for doing a more targeted search for materials, particularly if you're going to do experiments. You should not be misled into thinking that this excitation energy that you measure is actually measuring the gap. It's measuring something else, right? And we think that in order to kind of sort out this mess of possible materials that have metal-insulator transitions, this sort of insight will be important. Okay, so in the remaining time, I'd like to move to my second case study. So let's take a deep breath and see whether you still have patience to hear about something completely different. The role of point defects in non-radiative recombination. So here's a semiconductor. I told you I want to talk about materials that are relevant for light emission. So how do we make a light emitting diode? Well, we inject electrons in the conduction band, holes in the valence band. We want the electrons and the holes to recombine by emitting a photon with an energy equal to the band gap. And that's radiative recombination that gives us the desired result for our light-emitting diode. Now, that does not happen with 100% efficiency. And there are a number of loss mechanisms that can occur that reduce the efficiency. But here's an important one, having to do with the presence of point defects in the material. Now, I use the term point defects very generically. It could be like a native defect, like a vacancy, a missing atom, or an interstitial, an extra atom in the lattice, or it could be an impurity, okay, which may be intentionally or unintentionally present in the material. But very often, these point defects introduce levels into the band gap of the material. Okay. And when such a level is present, you can imagine that instead of an electron directly recombining with a hole, maybe the electron would lower its energy by dropping down to this defect level, okay? And then subsequently it can drop down over the other energy by recombining with a hole, or alternatively you could say, well, once an electron is sitting on the defect level, you're actually capturing a hole. Remember, holes like to bubble up in this sort of energy diagrams. You capture a hole, and that constitutes a full recombination cycle in which you basically lose an electron and a hole. They're not going to contribute to the radiative recombination. The energy of these processes essentially gets released in the form of phonons, in the forms of heat. You heat up your device without getting any light out. Okay. So this fundamental mechanism has been known for a long time. It's often referred to as Shockley-Reed-Hall recombination, and these gentlemen published papers on this topic in the early 1950s. Okay. And this is very well known phenomenologically, but a rigorous physical description and a rigorous description in terms of first principles computations has been lagging. Okay, and that's what we focused our efforts on in the last few years, particularly because we are interested in addressing the limitations on efficiency in this very important material, gallium nitride. But what I'm talking about is actually more general. Okay, so how do we go about this in a physical description and for doing computations? Well, to figure out how important these capture processes are, you need to calculate rates, right? You can calculate the rate for the radiative recombination, and now you want to figure out what the rates are for capturing these electrons and the holes. And so the expressions look something like this. There are a number of factors here. Like for capturing an electron, one obvious factor is that the rate is going to be proportional to the number of electrons, right? Obvious. The rate is also going to be proportional to the number of defects that are in a charged state that is capable of capturing electrons. In this case, this is a neutral charged state. I'm assuming an acceptor type of defect that can be either neutral or negative. So when it's neutral, it can capture an electron, and the rate is proportional to the number of such defects. And then here's the quantity that we're actually aiming to calculate. It's the so-called capture coefficient for electrons at this defect level. And you have a similar expression for the holes. Okay. Now, for this process to be important, and by important here I mean to actually play a big role in non-radiative recombination, which is a bad thing, okay, but that's what I mean by important, to kind of actually be relevant. For this process to be important, you need high capture rates for both electrons and for holes. Okay, these are two separate processes, and both of them need to be fast in order for the overall process to be fast. And you can see that quite easily by thinking about a scenario where, for instance, the capture coefficient for electrons is very high. Okay, so this defect is going to capture electrons very easily. Okay, but then if the capture rate for holes is very low, then these electrons will just sit there, right? This defect is going to act as a very efficient electron trap, which may be bad for your device in some ways, but it's not going to act as a recombination center because those electrons are just going to sit there, and it's only by subsequently capturing a hole that you actually would complete the recombination cycle. So, in order for both of these processes to be balanced, you have to look at the overall rate of Shockley Reed hole recombination, which in 2 lines of math you can actually find looks like this, which is an expression that shows that, yes, the rate is going to be limited by the slowest of the 2 processes. Okay. Now, this has important consequences, which were pointed out already in these papers in the 1950s. And these consequences have to do with the fact that the rate of these capture processes depends on the energy difference between the band edge, where the carrier initially resides, and the defect level. Okay. If this energy difference is small, if the defect level is very close to the conduction band, for instance, the rate for capturing electrons will be high. Okay. Hopefully that's kind of intuitive. I mean, we can explicitly show that by going through all the equations and doing the calculations, but I think it's kind of intuitive that if there is only a small energy difference involved, the rate is high. The larger this energy difference is, the lower the rate is going to be. Okay. Now, the same applies for the hole capture. Okay, which immediately tells you that based on this simple picture, the overall rate is going to be highest if this defect level is more or less in the middle of the band gap, right? Because that kind of equalizes the energy difference with the conduction band and with the valence band, and these rates are going to be relatively equal to each other, and that's what's going to give you the highest overall recombination rate. So that's a simple rule of thumb. Mid-gap levels give you the highest recombination rate, and this rule of thumb has kind of explicitly or implicitly been used to think about what the role is that defects play for non-radiative recombination. And in particular, I see that in the context of high throughput searches, people are using this rule for identifying which defects would be most detrimental for a device. Okay. So, well, it's a rule of thumb, but how good is it, right? Okay. I want to point out an example where the rule of thumb utterly fails, and where if you would use it, you would be utterly misled. And people have already been misled to some extent. This has to do with transition metal impurities. Here are the transition metals again, but not in the form of a bulk material, but as an impurity in a material. Okay. So for those of you who may not be familiar with silicon technology, in silicon technology, transition metal impurities are known as killer centers. Okay. If you have any transition metals present in your silicon, even though that's not for light emission, but even for transistor operation, they're going to lead to very high rates of non-radiative recombination. Transition metals are known to be really bad. Okay. So we were wondering about transition metals in gallium nitride because we hadn't really heard much about their role in non-radiative recombination. And actually when we started looking, it turns out that transition metals are actively used in the production of some types of gallium nitride devices. Not light emitters, but transistors, okay? In a transistor, at least some types of transistors, these high electron mobility transistors, you need a semi-insulating buffer layer, and in order to accomplish that, very often iron doping is used. So the idea of having a transition metal present inside the gallium nitride material is certainly not new, sometimes intentionally introduced, but there is also some information around about the transition metal impurities being present as contaminants. And that's not surprising if you think about it. For so-called hydride vapor phase epitaxy growth, the reactors are often made out of stainless steel. You operate this at high temperature in a corrosive environment because of the gases that you're flowing. It's no wonder that some of the iron from the steel might actually get incorporated in your gallium nitride. Okay, so this is not some academic problem. There is reason to believe that iron, for instance, could be present in gallium nitride. So, what is known about iron? Well, again, this is not new. There have been experimental studies for a number of years to identify the electrical characteristics of iron in gallium nitride. In particular, where is the level in the band gap? Okay, so a number of these studies were actually done in the context originally of using magnetic impurities in gallium nitride for the purpose of making dilute magnetic semiconductors. I think that technology did not really develop, but there was a strong interest at the time. And these are very reliable studies that establish that the defect level associated with iron is about half an eV below the conduction band of gallium nitride. The band gap of gallium nitride is about 3.5 eV, so half an eV to the conduction band, 3 eV energy difference to the valence band. Okay. By the way, I'm using a different notation here, which doesn't really reflect the charge state. It's the oxidation state, because in the context of transition metal impurities, that's the notation that people typically use. Okay. So this is a transition between so-called iron 3+ and iron 2+. Okay, so based on our rule of thumb, we said that only defects that have level near the middle of the gap would give you strong non-radiative recombination. Based on the position of this defect level, you would think that, iron is going to be harmless, right? Its level is close to the conduction band, very fast capture of electrons, the level is so far away from the valence band, this energy difference is so large, the capture rate for holes is going to be negligibly low. You don't have to worry about this in terms of non-radiative recombination. That's what the simple rule of thumb says. But then there were some interesting experiments by the group of Solius Marcinkiewicz. He was actually visiting UCSB and did very nice photoluminescence, time-resolved photoluminescence on samples that were intentionally doped with iron. And he found the very surprising result that, well, okay, electron capture rates are high. Okay, this is a high number for an electron capture rate. But the capture rates for holes were equally high. So the rule of thumb doesn't work. The rule of thumb would say that this number for holes, Cp, should be orders of magnitude smaller than the capture rate for electrons. And it's not. So what's going on here? Is the experiment wrong? But if the experiment is right, how can we explain this? Okay. So again, I want to come back to the message that I want to convey here. You have to be very careful about understanding the fundamental physics, right? I won't have time, obviously, to guide you through the entire study that we had to do to understand this. I will only give you the answer. And the answer basically is that this consideration of a single level associated with iron and focusing on where it is in the band gap, it's too simple. It's a simple rule of thumb that is not good enough to describe all cases. And in particular, what you need to do for the case of iron is to take excited states into account. Okay. So we went through the whole machinery of doing first principles calculations, but ultimately what mattered most was when we started taking into account that for each of these two possible oxidation states, either 3+ or 2+, there are a number of excited states possible. Now, that's actually reasonably easy to visualize in the case of a transition metal impurity such as iron. You have D states, right? And for these particular oxidation states, like for the 3+, you have 5 of the D states occupied with electrons. Now, without changing the overall charge state of the center, you can actually promote one of these D electrons to a higher lying state, right? Because you know there are 5 D orbitals, but each of them can be spin up or spin down. In the ground state, they're all spin up, for instance, but you can do an excitation such that you actually put an electron in a higher lying D state, and that leads to one of these excited states. To make a long story short, once you take these excited states into account, you can actually find a recombination cycle where holes are being captured with an equal rate as electrons. In fact, the entire recombination cycle, once it starts, proceeds entirely within these excited states of the iron impurity. The iron actually never goes back to its ground state. And overall, it acts as a very efficient non-radiative recombination center. Once we took these excited states into account, we calculated these electron and hole capture rates, and they actually agree extremely well with the experimental numbers. So we think we have solved the mystery why iron, in spite of not following the simple rule based on the defect level, actually acts as a significant non-radiative recombination center. And this is now an insight that's not just limited to iron. It turns out that for many possible defects, and just mentioning one here, it's actually important to take such excited states into account to explain why you can have strong non-radiative recombination even in materials where the defect level is not sitting right in the middle of the band gap. And actually, more importantly, I think, this now sends us the message that defect-assisted non-radiative recombination can be important even in materials with very large band gaps, right? Think back to the simple rule where you say, well, the defect has to be mid-gap. Why does it have to be mid-gap? Well, because the energy difference between the defect level and the band edge should not be too large. But if you think about it, that would mean that if you look at materials with increasingly higher band gaps, aluminum gallium nitride alloys, or even pure aluminum nitride with a 6 eV band gap, you would say, well, you never have to worry about defect-assisted non-radiative recombination because any position of the defect level will be so far away from the band edge that you're never going to get an efficient overall recombination cycle. Well, that's not true if you actually take the presence of excited states into account, okay? So again, this was my second example to hopefully illustrate that you should have a really good understanding of the underlying physics to be able to effectively screen for properties that are going to be relevant for the materials that you want to achieve. That's the message I wanted to leave you with, and I'll be happy to take any questions. Thank you.